Oh my god. Hi there, this is going to be a video going over workshop 1, and this will be mainly going over everything about alcohols, ethers, and a little bit of epoxides. And one of the things that we did here, we're going to start off with how to name alcohols. It's very similar to how you would name a alkane, but now we're going to treat the alkane or the alcohol as the priority instead of like the alkane. What I mean by that is let's just start off with this one. We're going to number it 1, 2, 3, 4. And just like how you would with a normally substituted, let's say like an alkyl halide, you would number it so that the alcohol is first or on the lowest substituent, right? So this is going to be 2-butanol. Sometimes or more often you might see like butan-2-ol. Either is correct, it's fine. Now, this one here, we always want to number the alkyl chain so that the alcohol is on the lowest substitution or on the lowest number. So it's going to be 1, 2, 3, 4 instead of the other way around, because the alcohol is highest priority here. So this is going to be, let's see, 2, 3 dimethyl. Oh my gosh, I forgot. Wait. I got, bute and 2-ol. There we go. Also, I'm not going to be going over all of this stuff because that is a lot of time. So I'll be going over a couple of these at a time. So this here specifically, if we have two or more alcohols, we're going to be using like diol or triol, etc. So we're not going to number it right to left because the first alcohol is on the first carbon. So 1, 2, 3, 4, 5. That's going to be 1 bromo, 1 bromo pentane, 1 3 diol. There we go. It's really not that bad. Really not too hard. So let's do this one here. How I like to do these, how I like to number these kind of what am I trying to say? Hold on. Whenever I'm trying to name these kind of substituents, I always like box them. Oh my god. If I'm trying to name these kind of things, I like to box these substituents and name them separately. So this is a sec-butyl. Oh my god. This is sec-butyl. This is a bromo. This is a methyl. And this is an alcohol. And so I can see that, if I were going to name it, I want to do it alphabetically. So bromo versus butyl. But when I go to number it, I'm going to do 1, 2, 3, 4, 5. Okay. This is because I don't start off with the alcohol here. Normally I would if there wasn't the sec-butyl, but because there's the sec-butyl or any kind of substituent, I want to number it so that I get the most substituents on the lowest number. If I numbered it here, it would be 1, 2, and then 4, 5, 6, and this is kind of like, that's a nasty numbering. So so really this is gonna be U before, no, it's R. Okay, 3 bromo, 1 sec-butyl. Remember that we alphabetized the B in the sec-butyl. Butyl, 5 methyl, cyclo, whoa, hexan-2-ol. That's how you do it. If we want to be more specific as well and include the stereochemistry, we also just figure out each of the stereo centers here. So this is going to be 1, 2, 3, 1, 2, 3. This is actually S, but it's R. So this is 2R. Oh my god. Okay. This is 2R. And since there's another one, I'm going to separate that with a comma. This methyl here, 1, 2, 1, wait, no. 1, 2, 3. That way. So it's going to be R. So 5R. And a dash in between. So 2R, 5R, dash 3 bromo, blah, 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 blah. Okay. So I'll go over those 4. And naming ethers, they're a bit different, so, but they're not too different. The way you would go about this is, since there's an oxygen separating 2 different alkyl chains, you want to figure out which one's going to be your substituent and the other one is going to be your parent name or parent chain. So since this is longer than just a methyl, I'll have this as my parent chain. While this is going to be my substituent. Okay. And so, oops. Okay. And so I would really just say like 1, 2, 3. So this is going to be methoxy. Methoxypropane. Methoxy because there's a methyl, and oxy saying that there's an ether or an alkoxy, right? When we go to this one, alkoxy substituents and halides are on the same priority, so we kind of treat them the same. So when we go to number it, it really is just before, like 1, 2, 3, 4. Number it so that your substituents are on the lowest number, right? We don't really care about the priority of alkoxies because they're, pretty low. So when we go to name this, it's gonna be, let's see, 1 chloro, 2 methoxy, 3 methyl butane. There we go. Okay. How about we do this one, where we have an alcohol and this kind of substitution here. So when we have an alcohol, that kind of changes the priority in how we name and number the chain. Normally, if we didn't have an alcohol here, so like let's forget there's an alcohol. If we didn't have an alcohol here, I would number it 1, 2, 3, 4. But since there is, I would number it the other way because we want the alcohol, which is way more important than other substituents, to be on the lowest number, 2, 3, 4. Okay, we're gonna name this as a chloromethoxy. Chloromethoxy. Okay. So this is going to be 4 chloromethoxy. Butanol. You could also say like 4 chloromethoxy 2 butanol. Though I believe that this convention is better when you're dealing with like things that kind of change the ending of the parent name. So for example, if I had like an alkene and an alcohol here, then it kind of changes into like 3, wait, let's see. It kind of changes into 3-ene, 2-ol. So that's why, I think that's primarily why that this convention is picked more or used more than older versions. Anyway, I digress. So the rest of these is for your practice. You can always check the keys as if you'd like. So now we're going into dehydration synthesis. And really the key things here is that sulfuric acid is a strong acid, and that means it turns into a weak base. let's write that down here. H2SO4, strong acid. Then it turns into a weak base. So HSO4 minus weak base. And so if you remember, if we have bases tend to do elimination reactions. And if we have a weak base, like alcohols, water, they like to do E1, right? So we're going to expect rearrangements or etc., right? So let's just do one with the sulfuric acid first. So the alcohol is going to deprotonate the sulfuric acid. Okay. OH2 plus. And the first thing that happens in an E1 reaction is that the leaving group leaves. Remember that OH2 plus is a good leaving group because oxygen does not want to be, a plus charge. It wants to leave and be better. So now we get plus charge here. And since we have a weak base, not necessarily a strong one, it gives us time to rearrange into something that gives us a better product or a better intermediate, such as this. Now we have a tertiary carbocation. Now our weak base is going to choose the hydrogen. It's going to pluck off the hydrogen that gives us the most stable product. The carbocation I would call is like the alpha carbon, and the ones adjacent to it are the betas, if you ever get mixed up. So the final product that we would get here is a tetrasubstituted alkene, which is very stable. And it's Zaitsev. Cool. On the other hand, if we have Pockle, a few things to know about Pockle, or like, here's the one thing that I think about when I see Pockle. Whoa, okay. CL, it's actually supposed to be 3. So Pockle 3. Pockle is actually a Lewis acid, and if you recall from Ochem 1, Lewis acids are things that accept things that accept electrons. So essentially they're kind of like electrophiles. So in this case, if we do that, it attacks a phosphorus and kicks off a chlorine, giving us OH plus POCl2. Okay. Pyridine here is going to act as a base to pluck off the hydrogen and neutralize it. This is pyridine. Okay, and then we get our intermediate here. Pockle is a good leaving group, but because we have pyridine, it's going to undergo E2. Usually when we talk about E2, we do get a mixture, but here in this case, we actually just get the Zaitsev. So whichever adjacent carbon has beta hydrogens, we'll pull from. So there's the alpha, these two are the betas. We only see that one adjacent carbon has beta hydrogen, so we're going to pull off from there. And then okay, H, and then we have, did I draw that? Yeah, I did. Then we have the Zaitsev product for this reaction. Not necessarily like the most stable of these two products when we compare them, but for this reaction alone, this is the most stable product we can get with Pockle. While this here on the left is the most stable product that we can get with H2SO4. Okay. They are both Zaitsev in the sense that they are the most stable products that you can get or is available. If that makes sense. So very quickly, when we kind of replicate what happened above, alcohol is going to deprotonate the sulfuric acid and form water. Water is a good leaving group, so it's gonna leave. It's gonna dip. And since we formed a weak conjugate base, we're gonna do E1. That's kind of like the kicker. If you have strong acid, it'll become a weak conjugate base, and that's how you know we're gonna do E1. Okay? And that is how you know you can do rearrangements and form a Zaitsev product. H2SO4 is a catalyst. So usually I will use HSO4 minus to deprotonate the beta hydrogens and regain that catalyst. It's just what makes sense to me. Sometimes you'll also see people deprotonate with alcohols or water. That's not necessarily wrong. That's always expected. I just think that using the catalyst to deprotonate back, it just makes sense for me. So if we do the same thing for Pockle acts like a Lewis acid. It's going to get attacked and kick off a chlorine. Since it's E2 with Pockle, we're not going to get any rearrangements. Pockle 2, and then pyridine is going to deprotonate. Okay. Pyridine is going to deprotonate and neutralize it. Then another equivalent here of pyridine is going to take a beta hydrogen. And the only beta hydrogen that is available here is on this carbon. So, okay, it's going to snatch that. The bond here is going to make an alkene and kick off the O-Pockle 2, making the product. Notice that when we do abstract this hydrogen here and make this alkene, the stereocenter is erased because you need 4 different things around a carbon to make a stereocenter. Now there's only 3. Okay, keep that in mind. So really, the difference between using sulfuric acid and Pockle 3, is that sulfuric acid goes through E1, but this goes through E2. Both reactions produce the Zaitsev, but sulfuric acid allows for rearrangements. While Pockle 3 does not allow for rearrangements because it's E2. It's going to be fast. Okay, so let me know if you have any questions about that. We're going to talk about Williamson ether synthesis. And this is kind of the first instance where you'll encounter disconnections for retrosynthesis in your organic chemistry classes. It's very simple, really. For Williamson ether, I know that you're going to start off with an alcohol and an alkyl halide, right? So let's just keep that in mind. Ether synth equals alcohol and alkyl halide. Okay. And since I want to work backwards from the product here and end up with my starting material, I know that I'm going to end up back to an alcohol and an alkyl halide. So one thing that I like to do is just draw a box around the oxygen, and whatever is inside this box is going to be the alcohol. So OH plus, then whatever's not in the box is going to be my alkyl halide. Maybe I'll use bromine. Okay, so that's one set. The other set, I could draw a box around the other part and have that as my alcohol. And the other one as my alkyl halide. At its core, let's talk about this. At its core, Williamson ether synthesis is a typical SN2 reaction. And because it's an SN2 reaction, it has the same limitations as one as well, right? When we depronate our alcohol, which is the first step in a Williamson ether synthesis, typically with sodium hydride, we get an alkoxide. These are really good bases as well. So not only that are they nucleophilic, but they're also basic. And since they're a base as well, we have to be careful of any potential elimination products. This question, I'm not asking which set is favorable, but you can always keep in mind which set is realistically going to yield a good ether synthesis. So let's do the other one right here. Whatever's inside the box is going to be my alcohol, while whatever's not in the box is going to be my alkyl halide. So that's one set. Well, the other set could be that this aromatic is going to be my alkyl halide, and the other component is going to be my alcohol. Now, for which one I want to know is going to be more, or like, it's going to be better to use, is going to be the left one, because the right here, you can't exactly do SN2 with sp2 carbons. Oh my god. And even though on the right there are beta hydrogens, this can still do SN2. Still can do SN2 at a much more reliable rate than this set. Okay. So experiment with that. These two you can do on your own. Keep in mind the stereocenter. Okay. This one is pretty tricky, okay? But let's walk through it. We have an alkyl halide here. We have an alkyl halide, and I know that chlorine, as far as we've talked about it, acts as a good leaving group, okay? On the right-hand side, I see that there is no chlorine, so it most likely left. And interestingly enough, I see that this this double bond shifted. So there has to be some kind of interplay there. There has to be something happening there. What we can do is break this product down. So let's do that. Okay. If we break this down, this is essentially like this is essentially an ether, and so I'm going to break it down like an ether. I can get this one as my alcohol, and then I can get, let's see, this one as my alkyl halide, and this is exactly that. So if I were to break this down into two components, I should be seeing this in my synthesis. Okay. So going into the forward direction, how does that look? Okay. I know that we're in the first step, we're going to be reacting with water and sodium carbonate. Right, CO3, yep. Water and sodium carbonate. Water here is going to be, generally when we see water, we think that is pretty weak, okay? That means it's going to either be a weak nucleophile or a weak base. And here it's going to act as a weak base. Actually, I'm sorry, it's going to act as a weak nucleophile. Because since this is weak, we're going to undergo E1, right? That should be your first clue. If it's weak, probably SN1 or E1. Whoa, not E1, I'm sorry, SN1. And now I have this primary carbocation. And generally when we see primary carbocations, those are pretty bad, right? But it's actually not really that bad now because there's a double bond here. And what you can do with this is resonance. Now we have something that's way more stable than a primary. We got a tertiary. So when we have this tertiary carbocation, we can react this with the water. That's going to act as a weak nucleophile. I'm going to redraw this. And sodium carbonate earlier is going to act as a good base to deprotonate the water. Na2CO3. And I have one of my components that I need to do my Williamson ether synthesis. Look, I made this. Look what I have up above. I knew that by working backwards, I should be getting this alcohol, right? And that's exactly what I got. Now the next step is to deprotonate this alcohol. Maybe I should, yeah, let me use the whole space. Now the next step is that I want to deprotonate this alcohol, maybe with sodium carbonate again. That's always fun. And now I have my alkoxide for me to do SN2 with the alkyl bromide. And now we get this. That's exactly what I got here, okay? Easy. So the next thing that we're going to cover is forming epoxides with halohydrides. This is called a halohydride where we have a alcohol that's also bonded adjacently to a halogen, halohydride. Very cool. And epoxides are essentially just ethers, cyclic ethers. They're three-membered ethers, so they're very strained. And since Williamson ether synthesis is an SN2, that also means that epoxide formation, it also follows that. And for this, we want to make sure that the alcohol and the leaving group, which could be our halogen, are opposite to each other, or like trans, right? So, when we treat this with NaH, which is a very good base, you know, I still see students trip up on whether it's a strong base, strong nucleophile, etc. So whenever we see a metal, we think, okay, this has a plus charge, and the other thing um, that is ionically bonded to it has a minus charge. So this is really just H minus. Now we get the, what am I doing? Okay, yeah. We get O minus, and that's, there we go. And now we can do an SN2 reaction here. That leaves, now we get this, which is super rad. Okay. This one here. So the first thing that we want to check is, are these two substituents on the same or different sides? And if they're on the same side, we have to change that. So we will. First, starting out, if you're not yet comfortable with the idea of mentally rotating bonds, always draw a Newman projection. And the way I like to do that is make a dashed line through the carbon that I'm viewing. That's going to be my eye, stupid eye. And that's the most horrible advice I'll give. I'm just going to draw literally what I see. So this is going to be my front carbon, and the thing that is in the plane, I'm going to draw. So the front carbon here, right there, it sticks out on the bottom. The bromine sticking out to the left, or to the right, to the right, to the right. The other thing is sticking out to the left. Yes. The back carbon has a methyl that is directly pointing up, so I'm going to draw that. The alcohol is on the right, and the hydrogen is on the left. Interesting. Okay. Now, I'm going to rotate that so that the alcohol and the halide are trans or anti-periplanar to each other. So what I'm going to do is have the bromine here, and the OH here. Sometimes I like to draw them in the plane, and that's totally okay. It kind of, like, drawing these two in the plane actually makes it easier for me. So I know that these two are in the front now. So what that looks like is kind of bromine, it's up here, OH is down there, and now I have the methyls sticking out. Okay, and when we treat this with sodium hydride, we're expecting to get an alkoxide. Whoa. O minus. Whoa, 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 whoa. This does a backside attack now, since they're anti-periplanar to each other. And now we get this feisty looking epoxide. Awesome. Isn't that so cool? Anyway, enough epoxides. We're going to talk about predicting the products when these alcohols are treated with these reagents here. So hydrochloric acid, reacting alcohols with HCl, secondary and tertiary go through SN1, while primary and methyl alcohols, like methanol, etc., they react through SN2. This is because, like, primary and methyls, they actually have to go through SN2. They're not gonna make a primary carbocation. That's horrible. Okay, so when we go for secondary reacting with a HCl, this essentially forms a good leaving group that's going to leave. And so we can get a rearrangement. Chlorine, being a good nucleophile, can attack and make an alkyl halide. There we go. that really is what we're doing here. We're just going to predict the products. If you have a hard time predicting the products without a mechanism, do the mechanism. Do what helps, do what works for you. So we didn't actually talk about this in class, but it is mentioned in your book. Primary and methyl alcohols don't readily react with hydrochloric acid. When we go look through the halides, the nucleophilicity kind of decreases as we go up the row, or like the column. So chlorine is a weaker nucleophile than bromine and iodine. So since that's the case, it has to be activated by the zinc chloride catalyst here. So since we're predicting the products and we're expecting an SN2, we're going to do exactly that. The chlorine is swapping out the alcohol. For Sockle, we're also expecting that there's going to be a chlorine that is replacing the alcohol, but the difference is that we're changing, actually no, the difference is that we're going to be keeping the stereocenter. Do I have a mechanism for that? No, I don't, actually. I do not. Wow, this is a long video. Okay. I can see why he doesn't do these videos. It takes a long time. SOCl, okay. Right? Sockle acts as a Lewis acid, just like Pockle, but Sockle. SOCl. This Sockle with one chlorine is a good leaving group, but chlorine here is going to attack that and do SN2 from the back shot attack. Okay. And now we get chlorine. That's on a dash instead of a wedge. Same thing with PBr3, but for the shit chloride, TSCl, tosyl chloride, it works differently. Okay, so the alcohol is going to act as the nucleophile when it attacks tosyl chloride. Oh my gosh, it's so cool. So cool. Oh my god. Oh my god. This is tosyl chloride. And so the way this acts is that this is going to bond with sulfur and displace that chlorine. Okay. I'm going to abbreviate this as tosyl, OTS. Pyridine is going to deprotonate that, so pyridine. And then we have our leaving group here. Notice that when we convert the alcohols into different leaving groups, that with Sockle and PBr3, I didn't draw PBr3 because it basically is like Sockle, but instead of a chlorine, it's bromine. But when we turn the alcohols into these leaving groups, there's a difference in the stereocenter, right? Because with chlorine and bromine, the stereocenter is inverted because we broke this carbon-oxygen bond. But when we use tosyl chloride, the carbon-oxygen bond is still retained, so the stereocenter doesn't change. Cool. Very cool, very cool. I might stop there because that's all we talked about for class, at least for week, what is this, week 2? Yeah, week 2? Week 2? Yeah, I'll stop here for week 2. Maybe I'll make a video for these later on, but just for the content that we covered in this week, I will keep for this video. So thank you for watching. If you have any questions, let me know. If you need to email me for any questions at uw.edu. Edu. That is my email. Feel free to email me or message me anytime. Okay. Have fun. Thanks, guys. Bye bye. Hello. Oh my